Okay, it's being recorded. We can start.
Okay. So yeah, I will talk on string topology and homotopy skein modules. And it's actually, most of this is old work. I mean, you see, I have two references up there from 2001 and 2003. And this is, there are, of course, lots of names of people, I mean, behind that. Let me say this work is based on work by Joseph Przytycki. So I should mention him right away in the beginning. Przytycki, and then Effie Calfagiani, and also work of Calfagiani and Lin, who unfortunately also died quite a while ago. So Lin by himself, and also collaborations, I mean, of Lin and Calfagiani. There's also quite some I mean, of this is related to Vasilyev theory. So I might mention him too at this point in time. And yeah, there are a few things that I added over the years, but I never wrote them up. So one of the goals for me today is actually was to kind of like get back into the subject, and I hope I mean, feel free to interrupt and ask questions at any time, actually. But as I said, when you type them into the chat, I won't see them, I mean, because of the technical setup. So the plan will be maybe to talk like a first hour, I will give like a survey. In the second hour, I might talk a little bit more technical, and then there might be still some time for questions left over. So what I will do is I will first talk about homotopy skein modules. So I won't talk about skein modules in general. Then I will talk about a little bit about string homology or string topology, and how this is related to the homotopy skein modules. And then in the end of that survey part, so this is only talking about my survey part, I probably will talk a little bit about some examples already and applications. But I mean, but we're gonna see that might move into the second part. So throughout what I will talk about today, M will be compact, connected, and oriented three-manifold. So possibly with non-empty boundary. So I'm not specifying that. So if I'm not saying anything, then you can assume it could have boundary of any sort, actually. So we know that at least for closed, in the closed case and irreducible, so that, or prime case, that pi1m essentially determines the topology of the three-manifold. So essentially, and of course there are methods to go from a prime case, you know, to other cases, but I'm not really talking about that at this point. Later on, it might become a little bit more interesting. So essentially determines the topology of the three-manifold. But that doesn't mean that we really understand everything, because you probably know that knot theory, even in the three-sphere, is still a very interesting subject. It's related to three-manifolds in general, by surgery operations, and in many other ways. So something that sits kind of between studying knots and links up to isotopy in a three-manifold and practically the fundamental group on its own was introduced by Milner a long time ago. Milner in 1954 introduced the notion of link homotopy. So in link homotopy, you consider, let's say, oriented links in the three-manifold, and you may assume they are embedded, but we allow actually homotopies as long as they keep components disjoint. Homotopies keeping components disjoint. So in other words, you can think about link theory in the three manifold, and you allow crossing changes. But if you allow a crossing change, then only for distinct components. And this is, even though much weaker than isotopy, of course,
sorry. I think you mean for the same component, right? These two strands must be from
yeah. So of course, only for same components. You're perfectly right. I allow this for the same components. I will of course be interested in those for distinct components. That's probably my mental lapse. Thanks for pointing that out, of course. Yeah, so even though that seems, you're forgetting all this knotting information in the three manifold, it's still a very interesting equivalence relation, and there are still problems until this day which are not solved. Milner classified for what he called like Brownian links. So these are links where every sublink is actually trivial up to link homotopy in the three sphere. But there's not much actually which kind of followed up from Milner's work for understanding link homotopy in more general three manifolds. And even in S3, there is a classification known by Habecker and Lin. That was, I think, in 1988. But it's not that you have actually a complete set of invariants and a very easy way. It's an algorithmic way in which you decide whether two links are link homotopic. That requires taking so-called string links and studying string link invariants, and so there's many questions still that have to do with link homotopy in three manifold, and it's far away from being understood. Even two component links, which of course Milner could classify by linking numbers. He also classified three component links in the three sphere. In the three manifold, there's practically there are like, I think, two examples, namely the solid torus and RP3, where there are complete answers known, but and those were done by students of Koshorka quite a while ago. But in general, link homotopy, even for two component links in three manifolds, is not understood, which is quite surprising because it's a very obvious question to study, in my opinion. So let me talk about homotopy skein modules, which will be based on this equivalence relation, even though I think there are still many questions about what they actually measure. So these are more now invariants of three manifolds, then you should think right away as invariants of links in three manifolds. So what I call homotopy skein modules, you might say link homotopy skein modules. And so there will always be a commutative ring with an identity around, which I usually, there will be various kinds, so let me not specify that at this point in time. So let's say R, and the modules that I will look at will be free R modules on what I call H of M, where H of M will be the set of link homotopy classes of oriented and unordered links in M. that you consider links which are not ordered is kind of like more something that people do in knot theory, while people who study really directly the equivalence relation, like Milner, for example, he actually looked at ordered links, and there's quite some differences, and there's quite some interesting problems, as you will see along the way, that result from that. So then you divide by a submodule generated by skein relations. And these skein relations that I will look at will, they will come from various rings. The ring which contains most information in a certain way will be this one. And then there will be various forget homomorphisms. So you will here put z equals 0. You will put here q equals 1. And you will go here to the integers just. So you have also here z equals 0. You have here q equals 1. And then there will be a corresponding diagram of R modules, where R can be any of these rings. The relation I will tell you is on this level, and the other relations will just kind of like be determined by forgetting, by the corresponding forget homomorphisms. So this is the relation that has been set up by Przyczynski. I think he did that probably at the end of the 90s, actually. The case of Z was was known before. So these are called Q homotopy skein modules. And the relation is the one coming, it's the Hom-fly or Hom-flipped skein relation. So this is now Q to the -1 positive crossing, right? In an oriented 3-manifold, and that's where we mostly use the orientation of the 3-manifold for. You can talk about positive and negative crossings. So meaning that you think you're looking into an oriented 3-ball, and in that oriented 3-ball, you have your orientation, and then you look at practically you look at a plane here, and there's like a normal vector to that plane pointing towards you, and then this is opposite in that plane. The positive crossing means you're it's against the clock, counterclockwise. So you have this, and now you change that crossing, but it's only allowed now, of course, crossings of distinct components.
Sorry,
and then
these two pictures look the same.
It's not finished yet. It's z times.
Yeah, but you probably means a different picture, so that the crossing is really changed.
Yep. Okay. Yes. Of course, crossings of distinct components. Okay. So you have a positive crossing, you change it to the negative crossing, and then that's the skein relation. And what you do is you divide by the submodule, which is generated by all these relations. And now I have a corresponding diagram, if you want, of skein modules. So there's here what is called the Q homotopy skein module of Przyczynski, H of M. Then there is a module that was studied much earlier, actually at the beginning of the 90s, by Hosty and Przyczynski. So C of M is called the Hosty-Przyczynski skein module. So they're the relation, because we just put Q equals 1 as the Conway relation. So often I call that module also like it's the mod. That's explains maybe the notation C. I called it C because it's based on the Conway relation. Then there will be something here where I put just Z equals 0, but I still have these variables. So I call that L. That's something like, because it has something to do with some kind of notion of linking number, because I mean, what you do is essentially there's this Q, and that power of Q will somehow measure what happens when you actually change a crossing. And then last but not least, down here, you see if we put both Z and Q now equal to 0, we practically do not measure anything anymore. This just becomes homotopy of links, not link homotopy of links in the 3-manifold. And so we know what that is, right? I mean, because if you take a link you know, if you look at links up to homotopy and forget any crossing information at all, so what do we get? We get the free abelian group, if you want, on H of M. I could do it like that. So this was still the link homotopy classes, but then you divide out by K plus minus K minus, now actually for also for crossings of different components. So what you just get is a homotopy of unordered links in a 3-manifold. And in order to kind of like say what that is, well, there's of course the fundamental group, and then there are conjugacies in the fundamental group. Let me call that pi hat of M. So this is conjugacy classes in pi 1 of M. And if you have a link with a certain number of components, an unordered link, I think of that as an element in monomials in pi hat. So let me abbreviate that to be pi hat, not carry the 3-manifold along all the time. And there is, of course, a mapping from, if you want, link homotopy classes in the 3-manifold into the monomials, which forgets the fact that we want to keep component disjoint. And so what this really is here is actually just the free abelian group on the monomials of pi hat, right? I mean, so you take the free abelian group generated by link homotopy classes, but then you forget practically the link homotopy relation and consider just homotopy. And what you end up with is, so I hope you can see that this is just the free abelian group on monomials of pi hat. So because this will come up a lot, so this is monomials.
I'm sorry, may I ask some questions?
Yes.
What do you mean by monomials?
Well, monomials are just unordered sequences, if you want.
An
unordered sequence of elements in pi hat. And I mean, typically, you know, if you think about like a monomial, you know, it's formal monomials, if you want. You're not multiplying anything or something like that. It's just unordered sequences of elements in pi hat. It's a way to think about them.
We have 3 non-abelian groups generated by the set of contiguous classes.
Oh, I don't understand what you say.
Yeah. So by this group of pi hat, we mean the 3 non-abelian group, or maybe the 3 monoid generated by that set of.
Yeah, it's the same thing. Same thing. Commutative monoid. Commutative because we allow things to commute with each other.
Okay.
Right, same thing. So I mean, you could also say free whatever commutative monoid. On this, same thing. Okay.
Okay. Now, sorry. I was already lost before that. Do you use 2 different letters H, or all of them are the same?
H of M is the set of link homotopy classes of oriented unordered links in M. That's this H. There's another H, which is the skein module, the Q homotopy skein module. So it's a different H.
So that in your diagram, this H is a skein module, right? in the square diagram that you have. This is
Yes.
our diagram of skein modules.
Yes, here on the right-hand side, I have like a diagram of skein modules, right?
So,
and on the left-hand side, I have, these are, of course, because they are modules over different rings, those homomorphisms that I have there are actually those induced by mappings of rings, if you want. So like the most important one probably will be on the left-hand side. So that is this thing, right? So where I kind of like have Q equals 1, if I have Q equals 1, then of course this relation for distinct crossings becomes the Conway relation, right? The positive crossing minus negative crossing is just Z times the smoothing. And so you get a corresponding kind of homomorphism, but it's not, of course, I mean, you can make Z of Z to become a ring over this, and then you can make it formally to become a ring homomorphism, but I actually won't need that in my talk today. So this is really just think of this as maybe all abelian groups, and you just have homomorphisms of abelian groups in this case.
So the definition of this letter H, which you have in the square diagram, is it written above there? So that quotient 3 are modules on H of M.
That's the free ZQ to the plus minus 1Z module generated by link homotopy classes of links in M, and then divided exactly by those skein relations.
Yeah, okay, but that quotient is that second letter H, right? Or
it's a different letter H.
Yeah, but could you just write the definition of the second letter H so that?
So yeah, okay, I can do that.
So maybe you already have that definition. Yes, that quotient, isn't it? That
that's the
letter H.
Q to the plus minus 1 Z module. So you take the free module on H of M. So those are the link homotopy classes divided by submodule generated by these. Okay.
Okay, and what? Which free module do you mean? Countably generated or what?
Well, H of M is my set, not countably. I mean, there's nothing countable going on. I mean, when I talk about a module generated, so I mean, that's a basis. So you take finite
of
those things, right? So you take finite linear combinations of elements in H of M, and then you divide by these relations. It's an interesting question, actually, because there are problems with then later on expanding, and I mean, and you run into these problems practically, I mean, coming from, well, like, for example, thinking about what happens if I would have apply skein relations and would have to do that an infinite number of times. So link homotopy skein modules will actually avoid this because of something I will tell you in a moment.
Uwe, could you do some example of this?
Example. Well, what is the skein module of the 3-sphere? I mean, that's kind of like the easiest one, right? So it turns out that the skein module of the 3-sphere is actually free, and you will have one generator for each number of components. So example would be if M is equal to S3, and then that is something that is being proved by Prutitsky, if you want, or in the case of the Hosty-Prutitsky module by Hosty and Prutitsky a long time ago. So then this will be a free module generated by unlinks with, let's say, R components. And here R, I mean, the thing is, one of the things which will make my life more easy on the long run will be, I actually will include in the set of link homotopy classes an empty link. So usually I might say are bigger than or 0 components. Usually are bigger than or 0, but then that would include an empty link. So often you include an empty link just formally, and there's no link relation that actually includes that empty link. But I mean, but one of the things that it will actually help with is if I look at the free abelian group on the set of monomials, right? Then the free abelian group on the whatever the set of monomials of pi hat, then that will become the symmetric algebra on Z pi hat. I don't have that if I don't include an empty link, right? So there will be an empty link if you want, and an empty monomial.
Okay, so this was an example of C of M.
Well, it's an example of H of M2. It's also the same thing. I mean, there the module in the case S3, all modules are free.
But H of M is the set of linked homotopy classes, so there should be linked, not just unlinks, but also other links.
Yes, but the point is even though the skein relation, right? And we don't know what H of M is. You're right. But we know what H of M is. The point is H of M is based on all these link homotopy classes, but what this says is actually that you can use the skein relation, and you can it doesn't depend on in which way you apply the skein relation. But of course, since you can use the skein relation to change arbitrary crossings, when you change a crossing, you will create a link with fewer number of components. And in the end, you will always be able to apply the skein relation sufficiently long until you practically end up with unlinks of various numbers of components. So what you end up with here is like a type of polynomial, which besides the variable z q to the plus minus 1 and z involves an additional, let's say, u, where u stands for the unknot. And I mean, and there will be a whole bunch of possible, unknots that you end up with. Because as soon as you look at the smoothing, right, which comes up here, that will reduce the number of components. So it's an inductive argument. I mean, this will come up, of course, a lot later on in the more general setting, that essentially the point of link homotopy skein modules, the big advantage actually is that when you apply the skein relation, you change the crossing, which kind of like will usually be done in such a way that the link gets easier or gets closer to something that we define as a standard link. And you smooth, but when you smooth, you reduce the number of components. And so you can do inductive arguments for link homotopy skein modules that you could not do for isotopy skein modules, right? If you change a self-crossing in a link, then the number of components will go up and you have no control at all. And link homotopy skein modules is the only class of skein modules where you actually have complete answers. In all other skein modules, the problem I pointed out, I mean, whatever skein module it is, it's very difficult to get answers. I mean, there are fantastic results known, and people maybe heard about, the Kaufman bracket skein module, which is like one of the favorite skein modules people are considering. They're based on framed links with corresponding skein relations. They are intimately connected with topology of three manifolds, and there are results known, like for two bridge links. It has been proved by Conway how those skein modules look like, right? I mean, it's always kind of like a question anyway. What do you mean by how such a module looks like, right? I mean, I gave you an example here, so maybe that's why that question is actually very good. You see, the question when such a skein module is free is, of course, a very important question.
Uwe, can I ask about the example? This is not obvious that if you will do the skein relation, that at the end you get trivial link. It could be proved.
No, it's not obvious. It requires proof. Yes.
Okay.
But I understand what you are saying if you mean C of M, because in C of M you said Q equal to 1 and also Z equal to what, 0? Yes. Well, okay. Maybe Z for Z doesn't matter.
Q variable is invertible, so you can always kind of like you change crossings and you will kind of like pick up Q variables. I mean, you will end up in the end with practically for each number of unlinked components, you will end up with its own polynomial. That's why I said, really, this is really what you will end up if I have like H of S3. There will be a map, which is an isomorphism, and that's proved by Pshititsky.
Well, okay. So if Q equals 1, I understand that. But if Q, because indeed you can make any two links, even if they are not linked homotopic, you can connect them by some homotopy and sort of modular links with fewer components.
Well, if Q is not 1, it's just that I mean, in the expansion you pick up Q variables, but it's still then you will have whatever a Q to the 5th times a link. And you will keep on expanding that. I mean, you can apply the skein relation to that too, and you can keep on doing that. You see, it's the submodule generated by that. So you can have that relation and multiply that relation by any multiple of Q. I think that's what you're a little bit worried about, that it looks like I can apply that skein relation only like naked as it is. But you see, that can sit in anywhere. Right, I can multiply that by any polynomial in Z and Q, and I create a relation. So if I have some kind of power of Q times a link, then I can still apply the skein relation to that link.
Okay, I see.
Right, and so here the magic word, it's the submodule generated by those relations. Okay. Very good questions. Never thought about that in this way. So, okay, let's see. So yeah, one of the things that I wanted to kind of like have in mind, that I will do that a lot, and that I will have an empty link kind of like in the background. And there will be this mapping from H of M into into whatever monomials of pi hat, which I call the wrapping invariant, right? And where the monomials includes also like a 1, right? So there is no, then there would be no free homotopy class involved at all. So yeah, what are the problems?
I'm sorry, Uwe. So I think I now understand what you mean, but I think that people in the audience are actually not very much familiar with skein theory. So maybe if you draw some an example, a simple example, like starting with trefoil, how to reduce it to the trivial mode or something like.
Well, that would not work, right? I mean, it would be something like a hop link.
Maybe
by itself,
yes.
Not by itself will always be in the skein module equivalent, because every two knots are equivalents. So like in that skein module in S3, every knot is equivalent automatically to the unknot. I don't have to do anything. So
why is that? why is that actually? Why are every two nodes equivalent?
Because I allow arbitrary self-crossings. And the trefoil knot can be by just doing arbitrary self-crossings. You know, it's like looking just at a knot up the homotopy of this thing. And of course, a trefoil is homotopy right, just to the trivial unknot. Right. I mean, here that would be an example where we would do something, right? I mean, you would have here a positive crossing, right? And then you could say that Q inverse times this minus Q times, and now I change this crossing. When I change this crossing, this falls apart into an unlink of two components, right? So this is equal to Z times, and now I smooth this thing. But I mean, I can draw that and kind of like try to draw that smoothing, right? So here you smooth this thing. So all what is important here, that after you smooth this thing, you just get a knot. Whoop, you see, I knew that would happen. So that knot, of course, will again be homotopic just to an unknot. Right? I mean, if you smooth this crossing, you go from two components to one component, and every one component, every knot is always will be homotopic to the unknot in S3.
And so you express the Hopf-Link.
Yes. So now I can kind of like, I can say the Hopf-Link, for example, is, and I can multiply the whole thing by Q. That will be whatever Q squared times the two component plus Z times the unknot. Yeah, that's kind of the easiest example at all, of course, I mean, that you can imagine. But I mean, but you see how practically, yeah, this is, of course, non-trivial up to link homotopy, but in the skein module, I can evaluate it. And I mean, and I will show you a formula later on. Actually, there's a very, very explicit formula that has been proved by Prutitsky, and I could generalize it to more general three manifolds, which gives you an explicit formula how to actually calculate the image of a link in the skein module. It's like a forest type of formula. It's very interesting, though, I mean, that you can actually do that. So you can just take it and you can write it down. And it will only depend on pairwise linking numbers. You see, of course, the Hopf-Link has non-trivial linking number, so something's happening, right? It's not in the skein module gives you the same element as the two component unlink. They're different. So the Hopf-Link is distinguished from the trivial. Not very surprising, right? I mean, we know linking number, so this is not really a strong statement. I just want to make the point that there is information that is picked up, and this is one of the problems, right? I mean, actually, I want to talk about. So understand, I mean, I had this as the last question, but understand underlying link homotopy invariance. So we know, for example, in S3, even though the classification is really, really difficult, we know that the link homotopy skein module, even the strongest version, if you want, is actually only picking up pairwise linking numbers. It will not pick up any further information. So it's weak in some way. But in a general three manifold, that's why I mentioned that in the beginning, there's even the classification of two component links in an arbitrary oriented three manifold is not known. So there, it's still an interesting question. Usually, I don't know whether there's really any information beyond something like pairwise linking numbers. You see, in a general three manifold, pairwise linking numbers are not necessarily defined. I mean, there's, of course, you know, there's lots of stuff. I wrote a whole lecture note on linking numbers in three manifolds, essentially. And you know, I mean, like it's not all three manifolds will do the job. But then you may ask, well, if they do the job, or if you have linking numbers, let's say in the integers defined, does the image of a link in the skein module then only depend on pairwise linking numbers? or is there other information in there that's not clear? And even for two-component links, what is the image? So this is like, this goes in this direction. And I mean, and I'm thinking about it, and that's where actually results by students of Koshorka come into the game, who actually did some work on classifying link homotopy in three manifolds, which are not of the form just S3. Even in surface cross interval, that problem is not known. Even though the homotopy skein module, it's kind of like is known for surface cross interval, but there's no such nice formula for the for like the Hosty-Prititsky module as we have in the three-sphere. Okay, well, one of the problems is understand underlying link homotopy invariants, which means, well, you take a link and you ask yourself, right? You look at the class of this in H of M or any of the other ones, and what does it really depend on? And I will give you answers for that. I will give you, actually, as I said, this is the only type of homotopy, the homotopy skein modules are the only type where you actually have pretty much complete answers.
Sorry.
Yeah?
So how about the three sphere? You are saying that this homotopy skein module contains only the linking numbers in the case of the three sphere.
Yes. I will come back to that later. I mean, I didn't prove anything of that.
Yeah,
I'm just telling you.
It would be very interesting to see, maybe not the full proof, but at least an example with the Bromian rings, for example. So you are saying that the Bromian rings are equal to the trivial three-component link in this setting.
Well,
right?
the image. Well, you can do the computation. You see something. That it actually depends only on the pairwise linking numbers. I mean, I would tell it would now take me like whatever 10 minutes to kind of like do that example of the Borromean rings to change the crossings, right? That's kind of like the disadvantage of that. It's the three sphere is just a very, very small example in a certain way of results concerning the freeness of skein modules. And as I said, as I pointed out, I mean, the question on what it depends is something I'm thinking about, but it follows from results of Prititsky, essentially, in the case of the three sphere. I will write down the formula, and I mean, essentially, you could check the formula for the Borromean rings again, if you want, right? But let me put that later on, maybe in hour number 2. Right? Okay. Remind me when I come actually to that formula. I like that formula actually, because I feel this is like an overlooked, very important problem actually for these modules. So here's find suitable presentations. So, you have one presentation which starts with all link homotopy classes of links, and then you divide out by a submodule. That's of course not what you want. You want a set of sublinks, right? Like in the case of the three sphere, you take all possible unlinks. So you want to have a set of sublinks which will generate the skein module, and then you will have relations with respect to those. In the case of S3, it turns out it's free, but that won't be the case in general. So find suitable presentation with, let's say, in terms of a minimal set of generators. And this is, in this case, it's actually very easy to say what is a minimal set of generators, and relate the relations, if you want, relate the relations to the topology.
I'm sorry. Would it be correct to say that link homotopy invariants which are behind these skein homotopy modules are always of type 1. Does it make sense?
You think about Vasilyev theory?
Yes, yes.
Well, I'm not sure. I mean, the understanding of link homotopy invariance is like if for S3 there are results about, I mean, which link homotopy invariants in general are Vasilyev invariants, and there's also a result that essentially says, oh, only pairwise linking numbers are. So, but I don't think that all the link homotopy invariants here are type 1. I don't think you can say that. Let's come back to that later on.
So there was also some work about type 1 invariants in 3 manifolds. For example, by Kirk and Livingston, also by Chernoff and by some other people. I think Schneiderman, yes.
Yes, I mean they're like this. The technical setup of what I'm talking about really goes back to work of Calfagiani and Lin, and Calfagiani, and they actually build on work of Kirk and Livingston. Kirk and Livingston did the construction of these invariants, right? I mean, like type 1 invariants. How do you construct them? What are obstructions to construct them in arbitrary 3 manifolds? So I know their work, and then Calfagiani and Lin constructed like arbitrary, if you want. Calfagiani wrote a thesis, and she looked at what are obstructions to construct invariants of higher order, of arbitrary order, and looked at obstructions there. Those obstructions are singular tori that you will see in a second again. So if you do not have these singular tori somehow, then you can construct these invariants. Whether these invariants give rise to polynomials, that's a different question. So there's like a little bit of something like, you know, here, what you end up with is always polynomials somehow. If the skein module is free on a set of basis elements, then you know, you practically end up with a collection of polynomials, each of which is a link homotopy invariant, right? So you see that here, right? When I wrote up this, you should think of this as a collection of polynomials. For each power of u, you will have a polynomial. And that polynomial will be a link homotopy invariant. Okay.
Okay.
And I don't know, but I don't think they're automatically type 1 that you get here, even though you get, you know, only linking numbers. But I don't actually see a reason for that at this point in time. You know, they're like, you know, I mean, what you do is there you would have to see that if you extend the invariant whatever to you know, immersions with, let's say, 2 double points, right, and you apply the skein relation twice to those double points, that you get always 0. And I don't think that's the case. This will be important, and it comes in actually resolving 2 double points. There will be relations resulting from that, but they will usually not kill the whole skein module. Even though in the case of the homotopy, of the Q homotopy skein module, there's quite some stuff that will be killed by that. I can already say that. So anyway, I'm kind of like going far ahead of what I kind of like will talk about in the end. So question is, of course, here, torsion in the skein module, free skein module. So this is, these are the typical questions that you ask yourself. So let me tell you that there's always like a minimal, the possibility to pick a minimal set of generators. And essentially it comes from this picture here, right? Comes from this picture of skein modules. You see, if you ask yourself what is the minimal set of generators for any of these skein modules, remember I can always change practically the variables and get to the case where I have z of the monomials in pi hat or s z pi hat, the symmetric algebra. So I will not get away from the homotopy classes of the components, right? Whatever I do, I will need at least one kind of like link for each element in the monomials of pi hat, right? So if you look at an unordered sequence of three homotopy classes in a link, in the three manifold, I can pick a representative link for that, right? And that will be like something that I will consider to be a standard link. If I now go in any of these skein modules and I apply skein relations, I will never be able to kind of like get along with fewer generators of the skein module than one generator for each homotopy, for each choice of homotopy class of the link, where homotopy class means just you forget everything, you just keep homotopy, right? Because that information is preserved if I kill the variable set q equals 1 and set z equals 0. So if I could get away with fewer generators, I would get fewer generators of sz pi hat or this free abelian group on the monomials. And I know there are no fewer generators of that free abelian group than actually all the monomials in pi hat. So this is something that is very important. And it's important here that the variable z is not invertible. Otherwise, you kind of like may get into some trouble, even though you may first think about the whole theory for having the variable z not invertible and then go over to the variable z being invertible. If you know something about, the module with z being non-invertible, of course, you can get information about that other one. But this is, I'm just saying the setup is made in that way that I automatically get a, not a natural, but I get a minimal set of generators for my skein module.
I'm sorry. Somehow I don't understand where these monomials come from. So you had the free abelian.
You just take the free homotopy classes of all the components.
Yeah, but why don't you take just the free abelian group generated by those free homotopy classes?
Well, the skein module maps onto that. That's the point. The skein module maps onto that.
But why do you need the monomials?
Well, the monomials are a basis, if you want, of the free abelian group generated by definition. You cannot have fewer generators. You cannot have fewer generators down here. So you cannot have fewer generators anywhere there. That's kind of like all what I'm saying. If I could get along with fewer generators than one link for each, you see, and you're never changed when you actually apply the skein relation, right? You will always preserve, because if there will always be one of the links will always be a link where I just changed the crossing. So the homotopy class of that component will be preserved. Whenever I look at a crossing change of different components,
okay,
right?
So
if you do a crossing change of different components, this will have the same number of components, and the components will have the same homotopy classes. And here, what will happen will be the homotopy classes will somehow be multiplied in a way depending on where the crossing is, right? So since only the free homotopy classes are defined, and there is no multiplication of free homotopy classes in general, except when you're in an abelian case, right? I can't really tell you what the resulting free homotopy class is, but we will come to that problem.
Okay, I think I understand now. The monomials simply come from the fact that we may have several components in our link.
Right.
So
Right.
so each component gives a free homotopy class, and then a monomial corresponds to actually a link with several components, and then you take the free abelian group of that. Okay.
Yes. Yes. Okay. So there is a minimal set of generators. By picking a what I call standard link.
And is it possible to have some generalization with colored free monomial? Something which remember the component as before at the beginning after this job, or nothing possible.
What do you mean by remembering the component? You mean remembering the kind of like the smoothing where it comes from, or it's a try to understand the question precisely.
Well, I think the question is there a colored version of this theory where you have some components colored red and some components colored blue? And
I mean, I wrote a paper on Bordism skein modules where this is much more natural. In the case of link homotopy skein modules, because you still work with like you know, the distinct components, and even though the skein relation will in a very kind of like defined way reduce the number of components by one, there is no kind of like, I mean, I know what you talk about, but it does not really seem to be very natural in this setting. I wrote a paper on Bordism skein modules, which is based on, yes, colored links. So you have like various colors, and then you can define skein relations also in a very similar way there, and you can compute these skein modules for colored links. I haven't really thought about it, but it doesn't really feel very natural to do that in this setting. So you want like you know, components of the same color, right? You want that allow them to intersect with each other, and only if you have like a crossing of like two different colors, a skein relation will act on. As I said, for Bordism skein modules, so where you allow homologies, that was something that very naturally came up, right? Because there, if you have two components, right? And I mean, for example, when you do a crossing change and you smooth the components and you think about that doing, I mean, going backwards, if you want, then it's a very natural way to think about. Then you create like new two components of the same color, which now have the same color. We're never doing that. We're actually never taking whatever z times something and apply the skein relation backwards. You're gonna see that. But this question is in the background.
But I think you can also do it in a different way. You can have the skein relations only for components of this, only when you have a crossing of components of the same color. So you allow self-intersections of any components that is always allowed.
That you can do that. And as I said, I mean, for what I call Bordism skein modules, where you actually kind of like what you do is you have like links, you look at links in the three manifold, but you look at them up to homology. And then you can, it makes very much sense in that setting actually to just talk about colored links, right? So you have like links, you have like a whole bunch of components like of a certain color. And I mean, you consider them up to homology because that practically means you now would allow to join two components. And so you can play with the number of components there anyway. in this link homotopy setting, it will be, you can do something like that, but I think it will only make the story more difficult. It won't make it actually easier. You can, and as an afterthought, after you have practically calculated these ones, you might kind of like talk about, yeah, what happens, I mean, if I, for example, have like a red and a blue color, and I consider that in a three manifold where red colors are allowed to intersect themselves and the other ones are not. This is like, I'm going to say that it's a different setup, and yeah, but this is not what link homotopy skein modules are typically defined on and have been considered. So as I said, I mean, I probably thought about this kind of like being colored when I thought about the Bordism skein modules. So I wrote a paper on that, but I didn't kind of like bring it up in this setting. I probably don't remember. It's one of these other papers that are like 20 years ago when I wrote them. So let me go on. So you have a minimal set of generators by picking what I call standard link for each alpha. So for each sequence of free homotopy classes, you just pick one. Usually I will call such a link K alpha. For the presentation results, I will be talking about, we want to kind of like pick them in a very specific way. Pick the collection of these links K alpha. So that will now be an element in HM or a corresponding representative if you want. I mean, actually I should write class of K alpha, then it's something in H of M, but I actually pick a representative link. So here's like in a special way, and I mean, and why I pick them in that way will not be visible until I talk a little bit more about actually the proofs and the problems that are involved in these proofs. One of the things is I want that every sublink of a standard link is a standard link. I also want that if some, let's call it A in, or its inverse, and inverse makes still sense on the level of free homotopy classes, appears. So in alpha, right? I mean, there might be a couple of them that appear. Then I want them to choose the link, and let me just draw the picture. I want to choose them parallel in some way. What will be important will be that there's an isotopy in the three manifold that will interchange then components, right? I mean, you may have a link that has where you have two components with the very same homotopy class, and then I want that the corresponding standard link, I can switch the components by isotopy, right? So here I would have like, let's say A, here I would have, let's say, another A, maybe here I have A inverse. So you can, same free homotopy class in a standard link, I want that I can go from one, if you want, from one to the other one, that actually will be the same up to isotopy, and not just link homotopy. Okay. And trivial, of course, trivial conjugacy classes, I just want to put as trivial links in a 3-ball away from all the rest of the. So there will be some K alpha, there will be, so the K alpha will consist of some K alpha prime, where K alpha prime will consist of several components, but all of those will be non-trivial homotopy classes. So these 3 conditions I can easily realize, but you still have to think about it a little bit if you want. And the point is now that there is a natural mapping from SR, where R is one of these rings, as R pi hat of M to the corresponding skein module. And let me introduce maybe that's kind of like the symbol that kind of like any of HM, CM, LM. So there's a mapping that is onto there, which will take an alpha in here, right? Remember, this is just another way to write R of the monomials in pi hat. I can map that to the image of K alpha in the skein module. And I argue that this map is onto. And why is this map onto? Well, it's practically what we talked about before in the case of S3. What you can do is you do induction, right? So you start with a link with a number of components and with homotopy classes of components. And then what I can do is I can start changing crossings until I actually end up with the corresponding standard link. Because the standard link is homotopic, just as a as a mapping of some collection of circles in the 3 manifold, because that is homotopic to a standard link. Well, you apply the skein relation, and you expand it in terms of standard links in the end. And the induction comes in that whenever I apply a skein relation, I either stay within the homotopy class and then I go to the standard link, or I smooth, and then I get a link with fewer components. And by induction hypothesis, I know this will again be in, this will already be in the image. So that this is onto is just actually an induction. And I call this map, let's call this map sigma. So that's a map which practically just picks for each possible choice of homotopy that I start with, picks a representative link. So of course, the big thing is find the kernel of sigma. If I find the kernel of sigma, I have essentially solved the problem that I kind of like pointed out up here, right? Find the suitable presentation in terms of a minimal set of generators. I will never get at fewer than that set of standard links, and relate the relations to the topology of M. So the question is, what is the kernel of sigma in terms of the topology? And I will talk a little later about that, but here's like, if you want, is my main theorem.
Sorry.
Yes?
If M is the 3 sphere, then sigma is injective, right?
Yes, in that case, sigma is an isomorphism.
Okay, thank you.
Yes. There are no relations. And I mean, and this is the question, when is it free? And I mean, I will first talk about the theorem when actually exactly, and I kind of like, I have almost every word, if and only if, up to some weird questions, you're gonna see that. I mean, when actually exactly are these skein modules free? So let me start with A. So it turns out that the Q homotopy skein module is kind of not such a great choice because it's almost never free. It's actually free if and only if M is one of the, you can pick whatever you want there, homeomorphic, diffeomorphic, is either the 3 sphere, the solid torus, S1 cross S1 cross I, or S2 cross I, and otherwise not. And you probably notice that this is like, that all these guys look like a surface cross, S1 cross D2 is like whatever an annulus cross the interval. with pi 1/2 abelian. And that's not a coincidence. So in all other cases, there's actually torsion in the skein module. So this was really my starting point. I mean, that observation, because Krititsky had observed torsion in skein modules in various cases, and I try to understand, and I mean, and that led practically to the whole classification. So for the result concerning C of M, which is this Hosty-Krititsky module where you don't have a Q variable, that is a way more subtle answer. And actually, I don't have a 100% answer. What I know is the following, and I need some kind of like 3 manifold for that. Let me see. I should have probably, no, I didn't want to actually write it up before. So here's like some intermediate kind of like words about from 3 manifold that I will use. I will, for example, let M hat be M, and I cap off all 2 sphere, cap off all 2 spheres in the boundary. And I will say that a mapping is essential. That will be mappings of tori or 2 spheres. A map is essential if it is injective in homotopy. And then here's the thing. Here's the actual statement. If M is and this is called aspherical and atoroidal, and that means that all essential maps of 2 spheres or tori in M or into M, right, are homotopic into the boundary. So if you have a manifold which is aspherical and atoroidal in that way, then the Hosty-Krititsky skein module is free. And I know if it's free, I know it's free on some set of standard links, right? That's what I always mean when I actually say that. The converse is tricky. I know, meanwhile, the following. So let's see. If M has an essential 2 sphere, if M has an essential S2, so something like which is non-trivial, right? So essentially that means M is not irreducible. M is not something like S2 cross S1. There's torsion in that case. Or M is not a connected sum of things, right? So, I mean, if there is one, then M could be a connected sum of things. That's what I mean. So if M has such a thing, as an essential 2 sphere, not homotopic into boundary, I should probably have said if M is not aspherical, then C of M has torsion. If M is not atoroidal, so, and that's kind of like, there's like, I did run into problems with respect to singular tori and embedded tori, and probably experts in 3 manifold topology, they know all that much better. Then there is like one class of 3 manifolds which are like special ciphered fibered, where there is a difference actually between essential singular tori and essential embedded tori. So if M has a singular essential torus, so if M is not atoroidal in that sense, then C of M has torsion, except possibly, and I still have to check some cases there, except possibly when M is special ciphered fibered. And I will not explain actually the special ciphered fibered. You may have seen that or you may not have seen that. So in the closed case, that means that you have a ciphered fibered space with base S2 and at most 3 exceptional fibers. And so that's this in this class of 3 manifolds, there might be singular tori, and I have not been able to actually create torsion in C of M in some of these cases. So this boils down the special ciphered fiber case. For me to solve that completely, that would boil down to study conjugacy in certain Fuchsian groups.
Uwe, if you
Yes.
take rational homology sphere, then this theory distinguishes this case from the standard one, or if you take.
I will talk about rational homology spheres a little bit later on. One of the things is rational homology spheres. You have like linking numbers defined, but in the rational numbers, that's not necessarily sufficient. There are also rational homology spheres. Let's see, rational homology spheres. If it's closed
number are well defined.
All of H1 is torsion, and then I understand. I understand many things, but the real point really is the fundamental group, and it's not necessarily homology in all cases here. So rational homology spheres, I don't think you can precisely kind of like eliminate the problem by going there. You see, these leftover cases where I kind of like, these are still special ciphered fibered manifolds which have infinite pi1, because I actually need for torsion. The point is the following: if there is not a Z plus Z subgroup, then there will never be torsion. If you have an irreducible and but if there is a Z cross, if there is a Z cross Z subgroup, there might be torsion or there might not be torsion. That depends. And so you have to kind of like fiddle around with that. The answer for L of M, remember, that was when Q equals 1 and Z equals 0. That is a much more smooth answer. So this is free if and only if each essential, if it's essential singular torus is homologous into the boundary of M. So these are kind of like, I hope you see, these are the obstructions. And besides some kind of like very small cases, there's like this answer is essentially complete and telling you when is such a skein module, a homotopy skein module, free or not. And that's why I still think it's kind of like an interesting theory, because no such result is known at all for any. There are constructions known, though, and I should say that, for Vasiliev invariance by Calfagiani. She essentially solved the problem of constructing Vasiliev invariance in 3 manifolds, which is something like a dual theory. So you actually look at like homomorphisms on skein modules, because you want to have something that satisfies certain skein relations. So it's like a dual theory, but she avoids actually some of the problems that I have with my approach, but she gets invariance. So she gets invariants. She just does never know, for example, whether these invariants combine to polynomials or things like that. Like there is a paper, I mean, I might mention some kind of historical stuff once in a while. There's a paper in 1995 that was due to Calfagiani and Lin, which first appeared on the archive, and they claimed actually to have a polynomial, a Hom-Fly polynomial for links in three manifolds which have no essential tori, because I mean these conditions come up in the construction of Vasiliev invariants too, but that turned out not to work. In the published version, actually, that part was taken out because the argument didn't work. It's very, very difficult for isotopy skein modules to actually construct polynomial invariants of links, so satisfying certain skein relations. So Calfagiani and Calfagiani-Lin, they understood, and based on, if you want, the work of Kirk and Livingston, they understand pretty well, they understood when can you construct Vasiliev invariants? What are abstractions to constructing Vasiliev invariants? But how these Vasiliev invariants precisely are related to skein modules, that wasn't quite clear, right? I mean, they don't get actually the polynomials. So what I'm trying here is, for example, is to say with link homotopy skein modules, you get an answer for the polynomials, right? I mean, because this answer is pretty much complete. As soon as the skein module is free, you have a polynomial in the corresponding ring for each choice of homotopy class of components. As I said, I mean, I'm not really saying that polynomial is telling extremely very much, because I don't really understand too much about what are the link homotopy invariants that underlie the image of a link in the skein module in the general case. That's kind of like the, if you want, the thing which is not so nice. So my suggestion is,
can I ask if there is some relation between skein models and genus of nodes in manifold? Some genus is very is not fixed notion. It depends because the manifold non-sample connected. But anyway, some estimation of Ciphered Structures or something like this. Are there possible to get some result from this stuff?
I cannot imagine this to come from link homotopy skein modules. They are coming from things like isotopy skein modules, and I think based on the Conway relation, that's already something that is very promising. I know that Calfagiani wrote a paper on this. She comes up with power series invariants. That's what you come up with when you look at, if you want, isotopy. So then this kind of like, you know, my argument that after finitely many steps, you're done and you have expanded everything nicely, that is just not working. You have to go over to isotopy skein modules. And I posted a paper actually on kind of like, you know, the question is, you don't really know what is a minimal generating set of links in that case, because my inductive argument does not work for isotopy. It only works for link homotopy. And so if you look at isotopy skein modules, you don't know a minimal generating set in general. That is a big problem. So you can still start and develop theory, but then you would want to allow essentially what you kind of indicated in the beginning, something like infinite expansion, something of this sort. And so you then look at modules that are defined by itself in a different way. I posted actually a paper on that on the archive not long ago, which is precisely addressing that problem So you can still control relations in some way, but you cannot really compute the skein modules. And then you end up with power series invariants and no longer with polynomial invariants, which you may say is nice. I mean, it's okay. And these power series invariants, they say in the isotopy case, then they say something very specific about things like the genus of knots in three manifolds. But it's got to be restricted, right? I mean, because you know, ciphered surfaces you don't have in general, right? I mean, you need like null homologous components, I mean, for that to be true.
You can take ciphered surface with some estimation of intersection number with other component, not just pure.
If you're working
something in this direction
here, you can kind of like look at various, you know, whatever, you know, a multiple of this thing will bound a ciphered surface. Yes, I mean, I know all these theories. I mean, I actually wrote a lecture note on that. I should advertise. I wrote a whole lecture note on kind of like ciphered surfaces and what you can do with ciphered surfaces. And actually, but this has nothing to do with skein modules by itself. But for example, I defined actually a Conway polynomial for links in submanifolds of rational homology spheres. And that Conway polynomial actually is giving you information about the genus of links. So this is a lecture note published in whatever 1996, 1997. If somebody's interested, I can send a copy. But it's not really, that is, this Conway polynomial is also in a rational homology sphere. You have to be more careful how to define it. Right? I mean, but there's a way to do that. And in rational homology spheres by itself, it's actually, the theory is not that interesting. In submanifolds of rational homology spheres, it's more interesting. So I did something like, you know, in a certain way, there's some kind of, yeah, Calfagiani in her paper where she used these power series invariants that she constructs. She's doing things then in integral homology spheres that I also could do in rational homology spheres, respectively submanifolds of rational homology spheres, like generalizing some results of Charlemagne and Thomson about the genus of links in three manifolds. This is stuff. I probably have forgotten almost everything about it, but it's nice to remind me of it. So can we have a break maybe before I start talking about string topology, because I actually wanted to talk about string topology.
Sure, but can I have a couple of questions first?
Sure, go ahead.
You just said about a Conway polynomial for submanifolds of homology spheres. For example, if you have S3 and some link in S3, or maybe a singular link in S3, then you have the complement of that singular link. And so what is that Conway polynomial for that complement? Is it the usual Conway polynomial like you?
No, I didn't talk about singular links. I mean, no, I didn't say that.
Okay, but if you have a link or a singular link in S3, then its complement is a submanifold of S3. Yes? And so, and you have a Conway polynomial.
No, not that. No. I don't have a Conway polynomial for singular links. I mean, the Conway polynomial that I define is defined for links in submanifolds of rational homology spheres.
Yes.
And it lives in something different than just, it's not just a polynomial with coefficients in the integers. It's something with coefficients in some weird ring, which is like a universal ring with respect to defining linking numbers with specific properties, because the definition of this is still very much the same as the definition for, you know, so essentially still what you do is you look at null homologous links in there, right? You look at null homologous links in a submanifold of a rational homology sphere. If you want to define the Conway polynomial from ciphered surface, so if you want to actually do it geometrically, you still need linking numbers with very specific properties. And this is actually what I do in the lecture note. I kind of like say, okay, you can then kind of like define some linking numbers, taking values in some, either in the rational numbers or something more specific. And then you can use that to do that construction of the Conway polynomial for null homologous links in the submanifold of a rational homology sphere. And so I should be more careful, actually. That's the class of links where I define a Conway polynomial in a geometric way. And you need it in a geometric way, and you need ciphered surfaces, because otherwise you will not be able to relate it to a genus, right? Because when you talk about genus, you want to talk about surfaces spanning the link, and what is the genus of those surfaces. So you need a definition of the Conway polynomial in those terms. So like an abstract definition, like just from the skein relation, for example, will not help you to approach a problem like that.
So you need links in a submanifold of a homology sphere whose every component.
If I look at links in a submanifold of a Q homology 3 sphere, that in that case I can define a polynomial.
Arbitrary links, or you need the components to be
null homologous links. For null homologous links. Otherwise, I don't know how to get a ciphered surface, really.
So null homologous means every component is null homologous. Yes?
No, the whole link, I think, is null homologous. Yes, then the whole link is null homologous. Not every component. Because okay. I just need a global ciphered surface, right? I just need a global ciphered surface, and that ciphered surface will be spanning actually the whole thing. I don't need like ciphered surfaces for all of the components. So in that case, you can span in a ciphered surface, and then you can kind of like study the cycles on this, and you can do the whole construction if you have linking numbers defined in a reasonable way. And this is what I actually do. I study the exact setting in where you can actually define linking numbers.
Okay, so
linking numbers with very specific properties. They have to be like they have to meet some homological properties. Like if you have, like, for example, a two-component link, and if you look at the linking number of this and that, and linking number of this and that, and now if you join these two, the linking numbers have to add up. So there are some geometric properties of standard linking numbers, and you see this is a Bordism. So in the end, you end up with something like saying, okay, if I want to, for example, do this construction, it's a completely different talk I'm talking about right now, right? So this is like, this I did like in the 90s.
Okay, but if you have a submanifold of S3, and you have a link in that,
well, S3 is kind of boring, because in a submanifold of S3 you have linking numbers defined in the standard way.
Yes, but do you get the usual Conway polynomial of that link, or what do you get?
Well, yeah, you would get the same thing. You can. The problem is if you just work with a submanifold of S3 and you look at the link that is not null homologous, you can of course span surfaces into that link in the 3 sphere. But then what are the cycles you're supposed to consider then? If I consider the cycles on the whole stuff in S3, I get the same polynomial. Otherwise, I cannot do the construction. You see what I mean? So, you can, of course, if I take a link in a submanifold of S3, I can span that link by surfaces in the 3 sphere. I can then do whatever the standard construction in the 3 sphere, and I end up with a usual polynomial in the 3 sphere. If not, I get surfaces that they give you like homologies from the link to something that sits in the boundary. And I can then study that. And that's what I'm actually doing there in a certain way. I can study something like these surfaces and the homology of those surfaces. Does that make sense? Right? I mean, if I have like, of course, let's say you have whatever a link complement, right? And so you're now having your link in that link complement, right? I mean, I can span that by a surface, and then I mean, I get if you want, I get a surface that spans both this thing, but it also kind of like it has boundary components in somewhere in this in the boundary torus of that kind of like knot, for example, that I've drawn there. And I mean, so you get a surface, but the whole theory will be very different, because it's a surface now that has like additional boundary components here. And you see, one of the things that makes it work, that you actually really have you have something that's in the end what you define. Let me tell it like that. In the end, what you get is you pick like a surface, right? And you end up with certain curves on this boundary torus. So then you can do the standard construction. You can say I define a Conway polynomial, but it won't be a Conway polynomial for this original knot. It would be a Conway polynomial for this link or knot, together with some curves in the boundary. Right? I mean, and that stuff in the boundary is also then, I mean, kind of like is not unique. But it's an interesting idea to kind of like really study that in detail. But essentially what I did, I mean, I looked at things that are null homologous from the start with.
Okay.
It might contain some components which are in the boundary too. And then you can, do the standard Conway construction and can get maybe invariants of, which are related to the genus. And that's the interesting thing. If you're interested, I mean, check my lecture note. I mean, I have like a section in the end where I exactly talk about how a generalization of the Conway polynomial then is related to the genus of links and Thurston norm and all these interesting things. Just has nothing to do really with what I'm talking about today.
Okay, thanks. And another question about the theorem which you stated before. So that theorem, if you apply it to the complement of a link or a singular link in S3,
Yes.
so are these conditions all satisfied in that case? Do you get the free modules?
Which conditions? I mean, like, then in that case, well, it depends on singular tori. There could be still singular tori floating around.
But the conditions are that this tori must be homotopic into the boundary.
If they are if all singular tori are homotopic in the boundary, and then there's no two spheres, okay, I mean that's not the case in this case, then actually the skein module is free. Yes. That works for manifolds with boundary. Yes, arbitrary. So in particular in this case.
So is there an example of well, if you have a split link,
everything that is hyperbolic, for example, will do the job. Because if you're in a hyperbolic 3 manifold, you actually do not have any z plus z subgroups. So my condition is automatically satisfied. So in hyperbolic 3 manifolds, you automatically have everything fine.
Okay, but if you have an arbitrary non-split link, for example, just a knot, does every knot complement satisfy your condition?
I don't think so, because you can have ciphered fibered complements, right? And I mean, it of course, I mean, it depends on what you're talking about. But if you're talking about if you allow, for example, ciphered fibered complements, then ciphered fibered manifolds, typically there will be tori which give you problems, right? Because you think about a ciphered fibration, right? You have like a base surface, Let's think about an orientable surface, and then you may have a curve, and you can actually look at the torus over that curve. And then there will be other curves. If they like intersect that in a single point, you automatically get torsion in the skein module, even in the Hosty-Pretitsky skein module.
All
Right? I mean, so this is, but you're right. I mean, that's kind of like the thinking, and that's the main idea. But I mean, but the distinction is really ciphered, fibered, and hyperbolic. And this is also what kind of like in string topology is happening. And that's kind of like the thing. When I wrote this first paper on presentations of skein modules, I had no idea about string topology, because I actually just came out from high school teaching, because that was my period when I was thinking about leaving mathematics and become a high school teacher. And I was just coming back, and in the time when I had been out learning how to teach high school physics and math, a string topology kind of like was developed, and it's actually quite intimately related to a kind of like finding the presentations, which means trying to understand what is the torsion, what gives the torsion in these link homotopy skein modules. It's very intimately related to string topology, and string topology has the same feature. It's kind of like non-trivial for ciphered fibered, and it's trivial for hyperbolic. And that's not a coincidence, because both things essentially study singular tori and intersections of singular tori with curves. Right? I mean, and that's kind of like, again, that gives actually my relations. But I now still really need a coffee.
Okay, so let's make a break. Then what time do we meet? 7? How about 7:05?
Okay.
All right. All right. See you then.
See you then. Okay. All righty. Yeah, I pulled here up the theorem where I thought that's kind of like might be the stuff you mentioned you might be interested in. So the thing is, one of the things that you have to be careful about is if you're working in an arbitrary 3 manifold, there's also not a unique choice of homology class of ciphered surface. So if you fix that, I remember that when I looked in there, well, you have to kind of like fix that. So what I call here, that's like from my lecture note, what I call Betti trivial just is a submanifold of a rational homology sphere. We can express that in terms of Betti numbers. And then I study something that I call ciphered structures, and that is really, you have an R together with a choice of homology class of ciphered surface. And then for that, you can actually define a Conway polynomial, right? But of course, for it turns out for null homologous knots, you won't have a ciphered structure, right? So I hide the problem if you want there. And then you have lots of things which are very similar. You know, you have a skein relation, you have the definition from ciphered surfaces. And like among other things, I proved this result, which is a generalization of a theorem by Charlemagne and Thompson for the 3-sphere. So that if you take links and you start whatever twisting and cutting, and then it tells you that, like, you know, things about the Thurston norm, essentially the Euler genus, the genera of the links, I mean, in the correct definition. So yeah, the whole book is kind of like on link theory and manifold. That's probably why I started to study skein modules. So it's hope thought I get to know the introduction is probably later on. So if you Google that, you can kind of easily download a free copy. It's somewhere out there. They're all out there.
Well, you probably know there is this Kojima's eta function, which is essentially the same as Cochrane's derived invariance.
Yes.
So it is defined by considering so-called linking numbers in the infinite cyclic cover of a knot.
Yeah.
But actually there is no, if you just take 2 cycles, they need not have, well, they consider the lifts, they consider the lifts of a null homologous cycle, but 2 such lifts, they don't necessarily have a well-defined linking number. However, the Alexander polynomial annihilates this module, and using that, so if you multiply one of these cycles by the Alexander polynomial, then you get something null homologous. This chain is null homologous, and then this chain has an intersection number with the second lift.
Yeah.
And then you can divide that intersection number by the Alexander polynomial to make it, well, actually, it doesn't have to be the Alexander polynomial exactly. It can be any annihilator.
There are
So-
plenty of questions. I never really, I had various breaks, right? I mean, like in my whatever mathematical career, like one of the breaks actually happened after I wrote that lecture note, because there were no jobs in Germany available. So I decided to go into high school teaching for a couple of years. And so when I left and when I came back from high school teaching, I practically went into homotopy skein modules about that topic. Before writing this lecture note, which is really my habilitation in Germany, I worked on things that Tim Cochran and Jerry Levine and these people were doing. I was as a postdoc at Brandeis, and I worked on high dimensional link homotopy. I mean, you probably know that. I mean, with Nathan a little bit, but my PhD thesis was also on high dimensional link homotopy. It actually started the difference between link homotopy in Euclidean spaces and link homotopy in spheres. I pretty much kind of like, I could do many things, but it's not really that big of an interesting problem, in my opinion, on the long run. I mean, it didn't really go anywhere. And I started off in immersions, actually. Right. So I had various breaks. I had like a break. Then after actually working on homotopy skein modules, I had a break because I pretty much went into administration at Boise State. And I have been for 13 years, I have been associate chair or chair, and my research has been running on minimal. So this is like, 2 breaks before, let me put it like that. So it's a while ago. So maybe I talk because I really have to finish actually before 11, because I have an appointment, as I told you, with an attorney, and I can't miss that appointment. Let me just try to talk a little bit about the relation with string homology. I mean, there's lots, of course, more technical stuff about like this theorem that I presented you and what the relations are. I mean, I can roughly say that there are 2 types of relations. One is actually coming from the fundamental group, and they determine a lot whether the Q homotopy skein module is free or not. And you can very, very precisely describe that. It's completely determined by whether the fundamental group is actually abelian or not. So if the fundamental group is not abelian, there will always be torsion in the skein module. I could also state it like that. But you see, it's well understood which 3 manifolds compact have abelian fundamental group, and there are very few. That's why you end up with that explicit short list that I had there. And what else? Yeah, and the others, all the other stuff is determined by singular tori. And I should not really take credit for that, because that was almost known to Kirk and Livingston already, right? The singular tori appear in the Kirk-Livingston paper when they study obstructions to define these Vasiljev invariants, right? Type 1 Vasiljev invariants already. So that singular tori would play a role, I think, is known for a long time, and that they obstruct the definition of invariance and thus obstruct the freeness of these skein modules was really not surprising. And I always have to be very careful to take kind of like credit for that. But I mean, but it's still surprising that not only that they obstruct, but that you actually can completely determine all the torsion in these skein modules. And so it's still interesting, because even though as soon as you have torsion, you may not get invariance, polynomial invariance, but you know the indeterminacy, right? So it's just modulo some, you get polynomials defined modulo something. Okay, so, but let me talk a little bit about how this related with string topology, which is a little bit more theoretical, and I will try to make it short and not too difficult. So I have to probably wave a little bit hands. So string topology is due to Chuss and Sullivan, and they wrote a paper in 1999 on that, which actually is on the archive but got never published. It was submitted to the Annals of Mathematics, but it turns out that in the general case that they were considering, there were some problems with realizing homology classes by manifolds, right? I mean, there's like some problems, and I mean, and so it turned out that some constructions in the paper did not work in the generality that was originally planned, and the homotopy theorists took over, and so that's kind of the history why that paper never got published. Just that you know that. I mean, there's many things. I am referring to that paper a lot in my paper, but the point is that I'm working in a very low dimensional setting where that problem does not appear. You probably know that the problem of that certain homology classes, or I could also say homology and Bordism practically is the same thing in low dimensions, right? I mean, that's all well understood. And I mean, and so whether you work in a Bordism setting or in a homology setting, it doesn't matter. And string topology has been formulated, for example, I mean, in the Bordism setting later on. But what's the point here? So what you do is you study mapping spaces, and what they do is they, for example, study maps from a circle into a manifold. And for me, you can still think about the three manifold. I don't want to define it in all generality. And then they look at what is called S1 equivariant homology of this. And let me just stick with integer coefficients for the moment, even though I will need a ring with one, a commutative ring with one in a second. And so that I'm not getting crazy with that, let me just abbreviate that in this way. So, well, what is S1 equivariant homology? So I'm not going to go into that. It's like you take whatever a product with some E, and so in general you can do it like that. But in my case, actually, it turns out that this is actually, you see, the only problem is maps which are constant. So this S1 action is by rotating in the domain, rotating maps in the domain. If you want me to kind of like write that up more explicitly, let me know. Right, so you have like a mapping from S1 to M, and you replace it by a map, whatever, Z times F, and Z times F will be F of whatever X times Z. So you have to be careful how you write it up so that you actually get an action of S1 on that mapping space. But essentially, you kick out parametrizations. That's all what you do. In a certain way. I mean, not arbitrary parametrizations are kicked out, but you allow, so one of the things that you will miss is practically a base point choice on the circle. So you will look at maps from a circle into the three manifold, but you do not really have control on the base point. But that action is free as long as you do not really have constant maps. And the constant maps you can kind of take out if you want. So I can actually work with map S1M, and I take out a few maps, and then this equivariant homology becomes a little bit nicer because it just becomes the homology of the quotient. It's just mappings from one circle at this point in time. So the quotient by that S1 action. And for me, what is interesting are like just two pairings that they defined. And I will try to define them in a second geometrically, but I will have to wave a little hands. So one goes from H1M and H0M into H0M. And another one that I call gamma L, this often I call just gamma, that will go from H1M into H1M. And you see, the relation to what I talked before should already be visible, because if you think of H1, right? Just think about H1 of maps, maybe the usual one. Then you can represent that by, you know, if you look on the chain level, you will, or identify that with Bordism, right? You will actually see one manifolds mapped into the mapping space from S1 into M, which is actually just a mapping from S1 cross S1 into M. So this is like the, you know, this you would call the free loop space, right? Of course, the space of all maps from S1 into M. So I should say that free loop space. So there are no base points floating around, and the singular tori are in Sullivan's work. So and he says it in his papers, but I honestly, I mean, at that time, as I said, I did really not know about it. I gave talks in Iowa, and the Charlie Froman, I should mention, he pointed out to me that my work on the presentations of homotopy skein modules would be related with Sullivan's work, and that's really how this kind of like work developed. So the point is, these pairings are just in their work, which is very general, are part of a graded Lie algebra structure on this homology, right? On for any manifold, they do that, and it's very general, and they generalize that actually then even to a Lie bi-algebra structure, which would take into account self-intersections, which certainly is related in some way to isotopy skein modules. And I have to refer to my recent preprint where I kind of like go a little bit in that direction, but I actually never finished that work. So the relation to link homotopy skein modules, though, is very explicit, and for that you only look at these two things. The Lie bi-algebra structure is more complicated, right? So here, this gamma L is a Lie bracket, and it's defined by intersecting singular tori, roughly. So roughly, this Lie bracket is defined as by, you take two singular tori, you look at their intersections, which will be a one manifold, right? I mean, because if you look at the singular torus, and if you look at another singular torus, right, you would get a mapping into M cross M. You can make that, right? So it's like one singular torus, here's another singular torus. Then if you look at the intersection, right? So you take the preimage of the diagonal, then you get a one-dimensional submanifold, which will be oriented and everything. And then what you can do is along these one-dimensional submanifolds, you can think of what is happening is only that one loop in the first family will actually intersect one loop in the second family in one point. You have to arrange that by transversality. So that's work, and it's not trivial at all. So, but after you've done that, because you have two oriented loops, what Sullivan is doing is just multiplying the loops, which is, of course, up to homotopy, the same thing as just smoothing the crossing. Right? I mean, if I kind of just am just interested in whether I actually first run through this loop and then run through that loop, that is the same thing than just smoothing the crossing and then doing the same thing. Up to homotopy, that's the same thing. Right? So what he's doing is multiplying the loops, which on a homotopy level just corresponds to, if you want, the smoothing in knot theory. So this is, for example, how he defines this Lie algebra structure. As I said, I will be doing much hand waving because it's not actually even easy to prove that it is a Lie algebra. So he's waving a lot. I mean, one of the things about what I'm talking about now is you don't have to worry too much about the S1 action, because it turns out that this mapping from S1 to M, right? There is a mapping into map S1M, a projection up to the S1 action. If you restrict that to mappings which are not constant, then it turns out you get an S1 bundle. And then for that S1 bundle, there's a Gaussian sequence, I mean, that you can study. And I mean, and from that Gaussian sequence, you see that on the H0 level, which is not surprising, it actually doesn't matter whether you look at equivariant homology or standard homology, while on the H1 level, at least I can represent everything. I mean, maybe I'm not writing everything down like that. So the point is, I will practically ignore for the moment now the S1 action. So the thing is, in the end, you have to be careful and you have to divide out by the S1 action, because in particular, when you intersect two one-dimensional families, right, this fact that you actually can nicely smooth along a curve without getting any problems, right? I mean, because you want to do this multiplication operation everywhere, that's a non-trivial thing. So, of course, in the general case, I mean, there's a second paper by Chas and Sullivan on closed string operators, and the story gets even much more difficult. But I will only need intersection of singular tori, and I will also need intersections of singular tori and curves, or if you want, like links in the three manifold. And so that you do, of course, a very similar construction. I mean, if you intersect a singular torus, but it's much more easy, right? Just with a map. So you have a singular torus in M, and then you get a mapping from S1 cross S1 to M. And then you have like just, let's say, one loop in M. So you get this map. And then if you take the pre-image, because this has codimension 3, so you just get a couple of oriented points in S1 cross S1 cross S1. And then again, you have to make sure that where I have these points, I will actually have just one circle in this family intersecting this. Right, and then again, you smooth there. That is what string topology is doing. I mean, they are multiplying, but I'm actually just smoothing. Okay, so let's see. So one of the things that I had to do is actually extend. So this is now the first homology of the loop space, right? So this is like, think of this, in this space, there live a singular tori. So I extend this mapping up here. And I actually haven't said that, I think. Oop. So this is a Lie bracket. And if you interpret what a graded Lie algebra is, you're actually gonna see that this first map, this gamma 1, actually just says that H0 is a module over the Lie algebra H1. So this is a module over H1 of M. So one of the things is to extend that, the whole story, first to well, to several loops. That's what you do. You know, a priori you have here H0. What is H0? H0 is actually Z pi hat, right? That's H0 of the free loop space. Okay, so this goes to Z pi hat of M. As I said, when I write M here, really, I mean this H0 of the mapping space, even maybe equivariant, but that's the same on the 0 level by some Gaussian sequence argument. So one of the things is to understand this extends to a mapping from what you do is actually you define whatever gamma of like I do that really. What I have to do is, yes, I have to kind of like explain what is this on an element xy, right? I mean, if you take like a product of two things in there, then this will be gamma of a tensor x y plus x gamma of a tensor y. Geometrically, what that means is just you actually, when you have like a singular torus, and now I have like two components, right? I mean, I just kind of like take the intersections with one, and then I add the intersections with the other. I mean, it just really means that, but I mean, it's kind of known when you extend using this type of Poisson identity that you now get a Lie algebra structure actually on this. And then I did something terrible. I defined something, but I mean, let me do that. So now this is a commutative ring with one. And this came by actually reading too much of Turayev's papers, because I should say maybe that the motivation for doing what I'm doing came from work of Turayev. Turayev wrote a paper on skein quantization in '91, where he interpreted skein modules of surface cross interval as quantizations, whatever that exactly means, of the Lie bialgebra, which was defined by Goldman and by him. So there is a Lie bracket, and then there is a co-bracket that was defined by Turayev. They together, they form a Lie bialgebra. And Turayev had a theory in a very old paper, very early, where he actually explained how skein modules, isotopy skein modules of links in surface cross interval can be understood as quantizations of this Lie bialgebra. So I was so much interested in kind of like doing this because this Goldman-Turayev Lie bialgebra actually is generalized exactly by Chuss and Sullivan to manifolds in all dimensions. So I thought, well, maybe there's a relation between three manifolds and the string bracket and the string homology in three manifolds. Even though it's tricky, right? I mean, it couldn't be the same because one of the things that, of course, Turayev is using is in surface cross interval, you have a multiplication. And that was, of course, an important thing, right? You stack links over each other. And I mean, and so there's a natural multiplication defined that made everything much more easy. But let me write up my definition. As I said, this is all motivated by practically trying to mimic at least partly or trying to do some construction similar to what Turayev was doing for surface cross interval in a general three manifold. So you take a homomorphism, and then here's a definition. I call a quadruple, sorry about that, A, alpha A, beta A, gamma A, with A and R module. So think of this A will be a skein module in a moment, with A and R module, a geometric R deformation of this gamma, where you may think of this gamma as the original one, which is exactly the one defined by Chuss and Sullivan, or this natural extension to where I consider possibly several loops and not just one loop. I intersect with singular tori. So if there is a commutative diagram where I take the R module generated by link homotopy classes, so this is like my old notation for the set of link homotopy classes of links in the three manifold. And then I have an alpha A to A. Remember, skein modules are exactly quotients of free modules on the set of link homotopy classes. And then I want to have like a mapping from that link homotopy skein module to S Z pi hat of M. Remember, that was the map that I had for homotopy skein modules before. And what I want is that this is the same thing as, well, here I can go to ZHM. And here I can, then there is, of course, the natural map here. That's kind of like coming from the wrapping map, you remember? Homotopy classes map to, yeah, so the free abelian group on the set of link homotopy classes maps to the free abelian group on these monomials, just another way. So this is induced by this homomorphism epsilon star up there. And gamma A, so there's this last piece. So this is just some compatibility, which kind of like says these things have something to do with skein modules. And gamma A from H1M tensor A to A, that's what this last piece is R linear, and is defined, and I have to say that what I mean by that, and is defined by a transversal version of the Sullivan construction, which essentially I could also just say means that well, I want it to be defined geometrically in the very much same way, but it will then say that this is practically makes the skein module to become a Lie algebra. A becomes a module over H1M, right? So a little H1M, I mean, you may just think of this is like yeah, those are the singular tori in the three manifold. That's all what I want. So that to say precisely what I mean by the Sullivan process, well, what that means is essentially you take something here in H1M, right? That's a one chain in the free loop space. Think of it as a singular torus in the three manifold, or linear combinations of those, right? And then my input here is now essentially something that comes from links, right? Because link homotopy classes of links by that map alpha A. And then the output will also be, you know, linear combinations of links. So, or link homotopy classes, I should say, because I never care about self-intersections, which is, I mean, you can avoid, I mean, and as I said, I mean, you can go ahead and can do these things more generally by also looking at isotopy of links, but it gets more difficult. So let's see what I skip here. So what I do then is I actually define something like what I call a universal geometric R deformation. And maybe I just indicate how that works. I mean, that universal version. That universal version looks at, and the whole motivation is coming from Vasiljev theory, if you want. You look at isotopy classes of immersions, isotopy classes of immersions with a single double point. And I mean, I guess you know that, I mean, you want that at double points. It's kind of like meets this condition that the two tangent vectors span a plane. And so you look at those, and then I look at various versions of them. I call them KIM. And I actually look at, with two double points. That's what I want. Away from double points. Yes, I want two double points. of this sort. So just imagine these double points kind of like look like this. They could be like that. So they could be like you have two components and you have like two double points in there, or you have like three components involved. So these will all be double points between different components. So I don't have like a chord that comes back, right? I mean, that's kind of like the stuff that you consider in isotopy of links. Or I could have something like this. So I call this actually K2. I call this K3 and I call this K4, depending on the number of components that are involved. And then I can actually think of it like this. So you have like this singular thing with two double points, right? So there's another double point somewhere. And you can look at the smoothings. So this is something in. And then I do the following thing. I smooth the first crossing and make it to become a plus crossing. And then I do this here. And then I do this. And then I do this. So you see there are two smoothings where I kind of like actually, no, so there's two changes where I smooth the second place and kind of like have a plus or minus on the first one. And then there are the other ones. And these I call integrability elements. Well, I didn't call them like that. I mean, that probably goes back all the way to Kirk and Livingston, if you want, and Kalfagiani-Lin. I mean, constructing things of this sort. And note that an integrability element that comes from K2, if I consider this to be in ZHM, so you see this is link homotopy. That means if I look at something like this, where I smooth, if I only have two components involved and I smooth one crossing, then actually I have created a single component. And I mean, and then the second spot is actually now self-crossing. So, and I mean, and for self-crossing, I can actually change. So this is actually 0 for K2M. But this integrability element turns out to be non-trivial non-trivial for K3 and also for K4. And what I then construct is something that is called WMZ, which is you take the free abelian group on the set of link homotopy classes of links in M, and then you divide by the subgroup generated by all K3 elements. So this turns out that if you do this, so if you actually divide out by certain relations, which come from considering, if you want the homotopies, you see, I want to have a pairing. That's kind of like the thing. I need this pairing. So in order for this to be well defined, I mean, I have to make sure that if I, for example, change that some stuff up to link homotopy in A, or if I actually look at the homotopy of that singular torus, that the result is not changing. So in order for that result not to change, I have to divide out by certain relations. That's behind that. And so what it turns out that this W that I define here is a universal geometric deformation, Z deformation, I should say in this case, where you just take for the ring, you just have the integers. And it's related to one of the skein modules I talked before. So I'm not really telling in much detail because I'm running out of time. This is like the universal Z deformation. Universal in the sense that every other, oh, it comes back. There's my internet sometimes doing that. So that every, if you have another one, then you actually, it's the universal Z deformation would mean if I had take any other Z deformation in this sense, it would map, the universal would map into that in the precise way. So with all commutative diagrams, you know, and stuff like that, it's not that easy to define, but it's stuff people like if they do like abstract constructions. But here's maybe the main point, which relates to what I talked about first, namely that C of M, remember, that was the skein module where I had no Qs. The Qs mess up actually everything. So C of M is a geometric R deformation of this Sullivan pairing for, well, epsilon being just what you expect, Z maps to 0. In particular, all requires proof, I'm sorry. In particular, there is this pairing gamma infinity from H1MR, right? R is, this is my R in this case. From and that H1MR is just H1M tensor product with R, right? Very easy to do that. I mean, we're anyway in the case where everything is like, I mean, isomorphic Königs by whatever, not Königs, the universal coefficient. So there is, it makes this Hosty-Prititsky skein module to become a module over a string topology Lie algebra, right? This is like a Lie algebra. And it becomes, in this way, there's a reason why I call that gamma infinity is. So here's another theorem. C of M is free if and only if this pairing is trivial. Right, so the action of the Lie algebra on the skein module actually is trivial. So yeah, I mean, there's, of course, I could talk another probably 5 hours about that, but I don't think it's worth it. It's something that I felt was interesting, and it's just like singular tori naturally come into the game in both this theory of homotopy skein modules. They also are, of course, around in more general skein theories, but they are closer. And I mean, and I can actually relate them more directly to string topology for homotopy skein modules. So I've been never able to actually generalize something like the full Lie bi-algebra structure for 3 manifolds of Chuss and Sullivan in the very same way like I did it with homotopy skein modules for the other case. My conjecture is it's something like if you look at a module, a skein module, which has actually uses split coordinates, because Turayev also has this situation. So like where you have this, where this is Z times this for a mixed crossing, and maybe U times this for a self-crossing. So skein modules defined in this way over a ring like this, that's my conjecture, that should be closely related to the bi-algebra structure, right? The bi-algebra structure is more sophisticated because it also looks at self-intersections of singular tori, which is natural, because what is that? It means you look at a family of circles practically floating around in the 3 manifold, and at certain points in time, there will be self-intersections. And what the Chuss-Sullivan process is doing, it's then smoothing, because what he's doing always, he's multiplying them at those points where that family intersects, which is exactly what you do in skein theory. So it's clear that these things are related, but there are certain things that have to do with this co-Lie algebra being defined in a completely, it's a completely different version, and I could never really generalize that in the way I wanted to generalize that. So because I have to leave like in 7-8 minutes, maybe I should write up the formula that I promised, this generalization quickly of Pretitsky's formula for the image of a link in the 3-sphere. And this is kind of like interesting. And I mean, but what I do will only work in actually, if you take a 3-manifold M, which is a submanifold of a homology 3-sphere. In a submanifold of a Z homology 3-sphere, like a complement of a link or not, or something like that in there, you have linking numbers defined in the integers. No problem, right? I mean, because in a homology 3-sphere, everything is null homologous, right? And so integral null homologous. So you actually can define standard linking numbers by, for example, intersecting something like a ciphered surface spanning whatever a knot with another knot, and I mean, and in the complement. And so you need actually, for what you're doing a certain way, you need linking numbers globally defined. Otherwise, actually, what I will say will not work. But what actually comes out of that, I mean, you can check that H1M is actually free abelian in that case. There's no torsion. Linking numbers in the integers are defined. And let me assume additionally, suppose that M is atoroidal. Okay. Then notice I have a mapping from pi at hem. I always have this. You always can map free homotopy classes into homology. And then what you do is, if you take a link L in M, an oriented link, I can assign to that a graph depending on L, but I don't give it a different name. Here's an example. Like you have there will be vertices, so that would be like the image of a 4-component link. So each of these, so these are a vertex for each component of L. And so you have defined linking numbers now between various components. And what I need also is the homology class here. So these are the homology classes under this map of the various components. So you have now an alpha 3 bar, alpha 4 bar, you have all these linking numbers, L14, L13, L23. So you get this complete graph, right? L34. Now notice I have a mapping from SR pi hat hem to SR H1M. And what I will do is I will look now at this. So this is remember, this is the Q homotopy skein module. So there are plenty of relations in there, and it's usually not free. But the point is, if I go actually over to homology, I kill these relations. But for that, of course, you have to study everything, and you have to look at everything. But it turns out that you can prove that there is a mapping in this setting here, where I kind of like map into SRH1M. So you're not getting a formula for the complete image in the skein module, but you can map the skein module into SRH1M, and there you get it. In Pretitsky's case, this will give you the complete one, because you see in S3 there is not very much. H1 is just trivial, right? So actually, I mean, there's only the unknot and all this stuff that you get from that. But here's the formula now for the image of a link. So this is rho. So you take the image of a link in that Q homotopy skein module, and then you map it into SRH1M, and that is a sum. Okay, so you sum over what you call full forests in that in gamma, and then it looks like Q to the sum. I just want to give you a feeling how difficult it is, even in simple cases, to write down the complete what is an image of a link in the skein module. Then you take a product over all E edges in S, and you have Q to the LE, and then you have something like quantum LE, which I may actually not really. What you do is you have to multiply in the end by, I must say that it's like something that I call gamma of S. So what's going on here is you have to pick like you know, this forest will consist of several trees. So imagine you look at a specific tree. So what you do is here is you this gamma of S is something that is in the monomials, if you want, in H1M. So you add all the alphas that come from there, right? So you you add all alpha bars in S, and this is just the number of elements in S. And even proving a formula like that is hard, even though the main thing is essentially what you do is you replace the problem of computing a link invariant by something that is called the dichromatic polynomial of a graph. So for this to work, you see, you do not really prove the formula immediately on the nose here. What you do is you prove that skein relations on the link give me certain relations of graphs, and then it's practically known that there is like something like a dichromatic polynomial, which is actually which is invariant under those relations. That's kind of like behind that. Okay, so this is just supposed to give you an idea, right? I mean, how actually something like that would look like, and this is, of course, the point here is it's interesting only for many components, but a problem I'm actually interested in at the moment most is what is in general for just two components. And this problem is not that, I mean, you might say it should be really easy, but it's actually not. The point is, if you have two components, just think about a two-component link in a three-manifold, and think about like up to link homotopy, right? So of course I can, if I now pick a standard link for that, right? You pick a standard link for that. So you have alpha is actually just like some alpha 1, alpha 2. So you have your two homotopy classes. I can actually make the first component to become standard by a link homotopy. I don't have to do anything, because link homotopy has this nice property. You can carry the second component along while you homotope the first component in whatever way you want, right? Whenever it kind of like has something to do with the second component, you just push the second component away. So people in link homotopy know that a lot. So, well, okay, now I have like this component. Now, the second component I cannot really control. But you see, I may think of the second component up to link homotopy. It looks like, so this, if this is K alpha, then I may say the second component now looks like, well, I shouldn't do that. It looks like, well, you kind of like, you go somewhere here. And so there are various meridians. So what I'm trying to do is then I try to study the second component in the complement of the first component. And that's related to stuff that goes all the way back to Milner's paper. Because Milner says that if you look at the complement of the first component and you let meridians of that component commute with each other, right? I mean, there are various meridians there. And these meridians are all conjugated, but they are conjugated by different elements in the group, right? I mean, in general, this will go through some very difficult group elements, right? So you have this, but the point I want to make is now is, well, how do I get it to the standard link? Well, you kind of change all these crossings, right? Whenever you change a crossing now, a new, practically what results will only be a knot. So it's not that bad. But you see, you have to collect information about the homotopy classes. So you see, this is something like a weighted linking number that you're actually looking at. Right? Because usually you would think of, okay, looking at all these points, right, where I now kind of like, for example, try to intersect, right? I mean, you essentially, you should think of now as an annulus that maps the second component to the standard representative, right? That cannot happen in general in the complement of the first component, so there will be intersections. So we look at those intersections of that annulus. But of course, there is an indeterminacy, and the indeterminacy will be given by comparing what happens along two annuli. And again, you end up with the same thing. You have a singular torus, you look at an intersection of a singular torus with the other thing, you're looking at intersection points, you're looking at kind of like, you know, what is happening when I smooth. So I'm sorry, I gotta go. Alrighty, but I just wanted to point out, I mean, that's kind of like what I'm actually thinking about in the end, because this is somewhat related with constructions of some of Koshorka's students, namely Alexander Pils. He wrote a thesis where he studied actually in surface cross interval. He studied linking numbers, and these linking numbers are weighted linking numbers. They use the fundamental group of the surface in order to define these linking numbers. And in my opinion, these linking numbers are what are picked up, at least in the homotopy skein module. They are picked up because the homotopy skein modules picks up the homotopy information of smoothing two components in a three manifold. I gotta go. Sorry.
Thank you very much. Thanks a lot.
All righty.
Interesting. Окей, ну, тогда заканчиваем. До свидания.
So it was very interesting. Thank you.
Goodbye.
До свидания.
До свидания.
Все, до свидания. Всего всем хорошего, с праздниками.
До свидания.
Да, спасибо. И вас.
Тем же самым.